Okay, hello, I am Sangori, a PhD student working at Vision and Learning Lab, Seoul National University. Today I am going to introduce ACAV100M, the largest yet video data set consisting of 100 million video clips with natural audio visual correlation. This is a joint work with Jian Youngjae and Professor Garni Kim from SNU, Thomas and Gal from NVIDIA, and Yale Song from Microsoft Research. So first of all, I want to set the stage by motivating why we want to learn from unlabeled videos. One of the great goals in the computer vision or machine learning is running perception in a way that humans and other biological agents can do. And that brings us to a question on how we learn to perceive the world. So if you look at the babies on how they learn to perceive, there are four essential components. They learn from dynamic and multisensory signals, and they interact with their surroundings, such as toys and their parents. And the most characteristic part of early childhood learning is unsupervised. That is, no one tells the babies that which is input and which is output. From this point of view, video is a very attractive data source for machine learning. It includes multimodal signals, including visual and audio streams, and even sometimes language in the format of captions. And we can teach an agent to learn physical interactions such as object manipulation and state changes within video environment. However, a lot of research in the field of video understanding has focused on fully supervised learning to make a highly specialized video system. We can easily see video detection and video retrieval models that are from humans. However, if we give the video retrieval model a video detection problem, or vice versa, the model will perform very poorly. I think this is not what we want, and we cannot say this is the right direction for understanding video. So, as a solution, many approaches these days are focusing on learning from unlabeled videos. The basic concept of self-supervised learning, many approaches are focusing on learning from unlabeled videos. The basic concept of self-supervised learning is that you design a pretext task that doesn't require manually annotated labels and train on neural net on unlabeled data from scratch. And once you finish this pre-training step, the run representation and model can be transferred to different downstream tasks by attaching some new prediction heads specific to different tasks and training this network on a target scenario. In this work, we especially focus on cross-modal self-supervised running between audio and visual signals. Then what is the strength of audio-visual self-supervised running? Let's take a concrete example. So assume that we try to solve the classification task. If we have images and their corresponding target labels, we can use some supervised algorithm to directly minimize the final error metric, that is the number of misclassifications on the training set. However, if the target labels are not available, we have to use some unsupervised algorithms, such as reconstructing input images. However, the run representations in this case are not well suited for classification because they have not been positioned to induce some optimal decision boundaries. So we can leverage cross-modal self-supervision in this situation. As shown in the right column of the figure, hearing mooing and seeing cows tend to occur together. So by utilizing this co-occurrence or correspondence, we process the moo sound to obtain a self-supervised label for the network, processing the visual image of the cow and vice versa. From this process, we can run discriminative representations. Recently, to utilize cross-modal correspondence, contrastive learning methods are often used. The goal of this method is to discriminate between different instances. By treating each instance as a distinct class of its own, we infer the features of audio and visual signals from the same instance to be similar, and contrast the features of audio and visual signals from different instances. The contrastive learning method have achieved quite competitive performance compared to supervised counterparts. However, we have some critical problem here. As you can see in the figure, the quality of learned representations is largely affected by the dataset size. Then our existing audio-visual dataset large enough? In fact, existing datasets for audio-visual learning contain at most 8 months worth of video clips. Compared to visual text datasets, these are smaller by orders of magnitudes. What makes this difference? While we can use automatic speech recognition to fully automatize visual text data curation, all audio-visual data creation methods so far have relied on some human workers so as to filter some noise correspondence between audio and visual channels. To make matters worse, we cannot scrape any random videos for increasing the dataset size, because some videos we can easily see online, such as music video, screencast, and news, do not exhibit some meaningful audio-visual correlation. So we have the following problem. We need to find a way to collect some good video data without any human efforts. Then what criterion should we use for automatic data construction? As I said earlier, recent self-supervised learning tasks leverage audio-visual correspondence. For example, a video sequence of a guitar player and the corresponding guitar sound. Therefore, we define a criterion that maximizes the correspondence between audio and visual channels in videos. More specifically, we define an optimization problem where the goal is to find a subset that maximizes the mutual information between audio and visual channels. Given a fixed subset size, our objective becomes selecting a subset of videos so that the mutual information between audio and visual signals are maximized. Here, the major challenge is estimating the mutual information between audio and visual features represented as high-dimensional continuous vectors. Especially, we need to do this in a scalable manner because we want to deal with petabytes of video data. Mutual information estimation method can be largely divided into instance and cell-level method depending on the granularity of alignment. Instance-level method estimate mutual information by aligning channels of a data point without considering the whole population. On the other hand, cell-level method take the subset of the population into account. Recently, the most frequently used instance-level mutual information method is InfoNCE. It first trains audio and visual networks by minimizing the objective on a random subset P to approximate the point-wise mutual information. Then it estimates mutual information between audio and visual channels for all videos in the whole population U, and obtain the desired subset S by taking the top S videos with the highest mutual information. However, it causes the chicken and egg problem. That is, it might get inaccurate mutual information when the train set P violates the audio-visual correspondence assumption, while our goal is to collect some subset with high audio-visual correspondence. Thus, we opt for using some cell-level method. Among the cell-level method, we use the classical clustering-based algorithm to measure the mutual information. Given audio and visual features, we obtain audio and visual clustering assignments respectively, and estimate mutual information by measuring the agreement between the two clustering results. Now we have all the components to solve the problem except one thing. How can we scale up the whole process so as to create data set from some petabytes of videos? There are two bottlenecks that keep us from scaling up, that is clustering and subset selection. First, the most popular choice among various clustering methods is k-means clustering. It is typically implemented using Lillo's algorithm. But as you can see in the figure, this algorithm needs to compute the distances of all samples from all k cluster centers at every iteration. So this causes slow convergence and some memory-intensive computation. However, we can easily compute the exact form of derivatives of k-means cost function. So, using this derivative, we perform k-means clustering with SGD optimization. This leads to fast convergence and small memory consumption. Second, since clustering quantifies the search space, our problem now becomes a combinatorial subset selection problem. As the problem is NP-hard, the greedy algorithm is often used as an efficient approximation. To further improve the scalability, we adopt a variant of greedy algorithm with the addition of the batch trick from some previous optimization literatures. The batch greedy algorithm randomly samples batch B from the remaining pool of candidates and searches for the next S elements to be included in the active solution set, that is the batch B. This batch trick reduces the time complexity to linear, that is O n times P, where n and B is the size of input data set and mini-batch respectively. Now we have all the components. We systematically evaluate our algorithm with some synthetic correspondence retrieval tasks. In each task, the goal is to discover the known corresponding samples among the non-corresponding pairs. This equals to finding a subset that maximizes the mutual information. We compared the algorithm against 3 embedding distance-based alternatives, and as a result, you can see that our method shows some reliable performance in retrieving synthetic correspondence, and especially it excels in the natural audiovisual correspondence task. We construct our curation pipeline around our automatic subset selection algorithm. So after processing collected videos, we extract features from pre-trained audio and visual encoders. Then we estimate mutual information between audio and visual modalities to select a subset of the original data based on the estimated scores. Now, to evaluate our pipeline, we scrape from YouTube 140 million full-length YouTube videos with a total duration of 1,030 years, which consumes 2 petabytes. To avoid redundant clips, we detect short boundaries using the scene change detector filter in FFmpeg and select up to 3 10-second clips from each full-length video that give the minimum total pairwise similarity scores. This gives us the initial data pool U of 300 million clips. Next, we run identical audio and visual networks in a self-supervised manner on the data sets produced using our pipeline at varying scales from 20K to 2 million. We also run neural nets on the existing data sets of the same sizes that are frequently used in the audio-visual learning literature, that is kinetic sounds of 20K, VGG sound of 200K, and audio set of 2 million. All these data sets were constructed with some careful annotation or human verification. We then attach our linear classifier encoders and solve the classification tasks on visual, audio, and audio-visual data sets. Across all scales, our data sets show comparable or even slightly better performances to the existing data sets. And the scales of 10 million and 100 million videos with our pipeline achieve the best performance. To assess whether our improvement does come from the initial data pool U or not, we also train the networks in the same way, but on the random sets of the same sizes. The significant gap, at most 10% point between our hours and random sets, shows that this improvement comes from higher portion of audiovisual correspondence in our data sets. We believe all these promising results show that our data set can provide a powerful self-supervisory signal. Finally, we conduct a user study to assess the perceived presence or absence of audiovisual correspondence in video clips. We compare clips from audio set, VGG sound, random set, and our data set. While there is still a significant gap between ours and VGG sound that heavily relies on some manual verification, our data set highly improves audiovisual correspondence over a random set, and it's even rated higher than manually verified data set, that is audio set. We released the largest audiovisual data set called ACAV100M. It consists of 100 million clips spanning 31 years in total, which is twice the size of How-To 100 million used for vision and language research, and shows the best performance in several downstream tasks. In addition to the scalability, the videos in our dataset show an incredible level of diversity thanks to the unconstrained nature of the creation process. Like many existing datasets where the videos are selected based on some human-defined taxonomy or some label categories, our selection process is based on a constraint optimization problem, and thus does not require any predefined taxonomy. And as you can see, this results in a much diverse set of concepts, some of which are not present in existing data sets. So we provide a data set and code base on our project webpage. There are also some explorers to examine our sample videos of the data set. So please visit our webpage, and that's all for my presentation. So thank you for listening.